We are glad to present our research from the Institute of Telecommunications and Global Information Space, NAS of Ukraine. Today, we will present our research titled Improving Data Rebalancing in Distributed Databases Using Adaptive and Elitist Genetic Algorithms. This work focuses on optimizing data rebalancing in distributed databases to improve performance and efficiency under high-load conditions. Our goal was to create a method that dynamically redistributes data fragments among nodes using a genetic algorithm enhanced with elitism and adaptive crossover. Problem and motivation. In distributed systems, data are split among multiple nodes. Over time, as workloads change, this distribution becomes unbalanced. Some nodes process more data and queries than others. As a result, query execution time increases and network traffic grows, leading to a noticeable performance drop. Traditional static allocation methods cannot adapt to such dynamic environments. Therefore, we propose a smart and adaptive approach that continuously analyzes the load and optimizes fragment placement to maintain balance and efficiency. Example of an individual. Before applying optimization, we need to represent possible data distributions. Each configuration of fragment placement is treated as an individual in our genetic algorithm. Here, the vector 1, 2, 3, 2, 2 represents the allocation of 5 datasets across 3 nodes. Different individuals correspond to different mappings, and the algorithm searches for the configuration that minimizes query execution time and data transfer cost. Proposed method. The optimization process is based on a genetic algorithm with elitism and adaptive crossover. Each chromosome represents a mapping between data fragments and nodes. The elitism mechanism ensures that the best solutions, those with the lowest execution times, are preserved between generations. The adaptive crossover dynamically adjusts its probability depending on population diversity. When diversity is low, crossover increases to explore new solutions. When diversity is high, it decreases to refine the best ones. This balance allows the algorithm to converge faster and more stably, improving both performance and reliability. Genetic algorithm operations, fitness evaluation, and crossover. Each individual is evaluated using a fitness function that measures query execution time and network load. The best individuals are preserved and selected for crossover to generate new offspring. This evolutionary process continues through several generations until convergence, forming an optimized and balanced data distribution. Implementation in Laravel/MySQL/Redis. The proposed method was implemented in a real distributed educational platform developed on Laravel, MySQL, Redis, and Docker. Laravel scheduler collects metrics such as fragment sizes, query frequency, and node latency. Redis stores these metrics as key value pairs representing the system's current state. The genetic algorithm is executed as a background service using Laravel queues for parallel evaluation. After convergence, a migration plan is generated and manually validated to verify the correctness of the proposed redistribution. In future work, we plan to automate this migration using write-ahead logging WAL to ensure data consistency and fault tolerance. Results and conclusions. Let's look at the experimental results. The graph compares the classical GA and our modified adaptive elitist GA. As we can see, the convergence becomes visible after about 10 generations, and the modified algorithm stabilizes much earlier. On average, our method reduced query execution time by 8.2% compared to static allocation and by 3.6% compared to the classical GA. Additionally, it achieved better load balance and lower variance across nodes, confirming the stability and efficiency of the approach. In the future, we plan to integrate real-time adaptive tuning of GA parameters and automate data migration within production systems. Thank you for your attention.